Okay, am I on? Can everybody hear me? Okay. Thank you, Martha, for the introduction and also for the invitation to come and present, give this presentation on the use of molecular chromophores in solar photoconversion. I'm going to make an apology right off the bat. I had originally intended to talk both about molecular photon upconversion and singlet fission, but when I was putting together the presentation, I realized that there probably wasn't enough time to actually do justice to both of those phenomena. So today I'm going to concentrate mainly on the photon upconversion. And with that, I'll get started. And first of all, acknowledge the people who contributed to the content you're going to see on the slides today. First of all, Professor Mike Furian and his postdoc John Huber Olivier from Duke University, who carried out the design and synthesis of some of the novel triplet sensitizer chromophores you'll see towards the end of the talk. Professor Phil Castellano and his postdoc Hyun-Soo Woo from North Carolina State, who have done most of the characterization and optimization of the molecular photon upconversion systems. As Martha said, the work that we carry out together is funded by a Department of Energy Sunshot Next Generation PV2 program. I also want to thank Professor Tim Schmidt and his group. A lot of the slides you'll see today, if you've ever been to one of Tim's talks, will look very familiar. He contributed some material relating to the photon upconversion efficiency and also device performance enhancement. So a quick outline of what I'm going to talk to you about today. First off, I'll discuss the Shockley-Queisser limit for a single junction cell, and then talk a little bit about what kind of performance enhancements we might see using molecular chromophores. I'll then discuss molecular photon upconversion, including the mechanism, some of the perceived limits to the efficiency of the process and why they might not actually be applicable. And I'll then go on to discuss using molecular photon upconversion for solar photoconversion. Show some demonstrations of enhanced photoresponse that have been carried out by Professor Schmidt. And then also discuss some solid-state molecular upconversion systems. That'll segue a little bit into the need to avoid the detrimental effects of oxygen. And then I'll talk a little bit about the novel near-infrared sensitizers that we've been working on. And so overcoming the Shockley-Queisser limit. So I don't have to preach the choir here, but a little bit on efficiency losses in a single-junction solar cell. There are a number of different loss processes, but the main ones we're going to focus on today involve thermalization and transmission losses. And these are particularly applicable in the context of this talk for amorphous silicon and organic photovoltaics, where the main loss process is due to transmission of sub-bandgap photons. Over on the right-hand side, you can see that for the best efficiency amorphous silicon and a couple of different organic photovoltaic active layers, you can see that we actually have some way to go before we even reach the Shockley-Queisser limit. But what I'm going to show to you is, in an ideal scenario, what kind of performance benefits we might get through the use of a photon upconversion process. And so to overcome these losses, there are a number of different strategies that have been employed to gain back some of the energy lost by transmission of low energy photons. Today I'm going to talk about photon upconversion. But there's also structures like the intermediate band solar cell. And then in terms of thermalization, as I said, I was going to talk a little bit about singlet fission, but I won't get a chance to do that. But there are other processes such as down conversion, multiple exciton generation in inorganic semiconductors, and hot carrier solar cells. In terms of the photon upconversion process, in an ideal system, we'd generate one high energy photon for every 2 low energy photon absorbed. This should compensate for at least some of the transmission losses in a single junction solar cell. And as I'll show you, the efficiency enhancements seem to be greatest for some of the wide bandgap semiconductors, and I've already mentioned amorphous silicon and organic photovoltaic devices. And we can see here in the plot on the bottom right-hand side, these are some calculations carried out by Professor Schmidt, where they consider a photon upconversion system coupled to a single-junction solar cell. And what you can see here is you can get a gain of about 1/3 in the power conversion efficiency for something like an organic photovoltaic device consisting of P3HT and a fullerene derivative. The benefit is not quite as great for amorphous silicon or some of the low bandgap OPV materials, but it's still significant. So to get to the actual process itself, what you can see in these pictures here is the emitted light in these molecular photon upconversion systems is emitted at a wavelength that is significantly shorter than the excitation light. So in this case, we have red to orange, and in the case on the left-hand side, green to blue photon upconversion. Why is this useful to us? Well, if we think about a single-junction solar cell with a specific bandgap, as I have already mentioned, we have transmission losses due to photons below the bandgap of the active semiconductor material. And if we can place an upconversion system behind that solar cell, harvest all of those low-energy photons, convert them to higher energy, and then direct them back into the solar cell, then potentially we can get some of those performance enhancements I just spoke about. In terms of the process of photon upconversion, there are a few different strategies, including the use of lanthanide ions for photon upconversion. But today I'm actually going to discuss a multi-chromophore mechanism where the active materials are actually organic molecular chromophores. In this mechanism, we have the absorption of independently of two low-energy photons by two different triplet sensitizers. Those sensitizers rapidly convert efficiently into the triplet state. That triplet state can then be transferred in energy to an acceptor molecule, and this is the sensitization part of the process. If we get two of these metastable, long-lived triplet acceptors come together, then they can undergo triplet-triplet annihilation to generate a single high-energy excited singlet state, and that can give rise to the emission of one high-energy photon. So we have two low-energy photons in, one high-energy photon out. In terms of actually applying this and getting optimum performance, there are a number of different considerations we have to think about in terms of the chromophores themselves. In terms of the sensitizer, we'd like the singlet energy to be lower, but the triplet energy higher than the corresponding levels in the acceptor. We'd also like rapid intersystem crossing between the singlet of the sensitizer and the triplet state so that we get a high yield of long-lived triplet states. For the triplet acceptor material, we'd like a metastable long-lived triplet state so that we can basically generate a huge reservoir of triplet states to undergo this triplet-triplet annihilation process. We'd like the singlet energy to be approximately twice that of the triplet energy. And finally, we'd like a high fluorescence quantum yield in the acceptor so that we can make as best use of all the high energy excited states that we generate. And then finally, there are a few energetic considerations on top of that. You can see that there are actually several different loss processes that happen throughout this mechanism. And so what we would like to try and do is minimize these energy losses while still maintaining sufficient driving force for these processes to actually occur. One thing that we need to do is to define the peak efficiency. If we start out with our original idea that we have two photons in, we can generate an encounter complex, and if that encounter complex gives us one singlet acceptor, that gives us essentially a photon conversion efficiency of 50%, and that's the peak photon efficiency that we can get. I'm going to define a conversion efficiency as the efficiency of the number of encounter complexes that give rise to a high energy photon. So in this case, one encounter complex, one photon, that's an efficiency of 100%. For those of you who know a little bit about spin statistics of this kind of process, we should actually be limited to an efficiency of 11%. And the reason for that is when two triplet sensitizers give their energy to the acceptor and we form these encounter complexes, we can get 5 out of 9 pairs occupy a quintet state, 3 would occupy a triplet state, and 1 would occupy a singlet state. And the general convention would be that only that singlet encounter complex can actually give rise to a singlet excited state that would give us a photon. So basically 18 photons in, 1 photon out, that's a photon conversion efficiency of only about 5%. So obviously not very promising if we want to use this for solar applications. But there's been some recent work by Professor Schmidt that experimentally in these upconversion systems, we find that the efficiency is actually significantly larger. And if we think about something like photodynamic therapy, where a triplet and a chromophore reacts with triplet oxygen, we can produce singlet oxygen at very high quantum yields. And so maybe this is telling us something about the accessibility of these quintet and triplet encounter complexes. So if we think about this, the spin statistics again, and we consider that our quintet encounter complexes are closed, i.e. that we can't actually access them, and that the triplet encounter complexes would decay to give one of the molecules still in its triplet state, then we can actually work out that the conversion efficiency is around 40%. In an even better scenario, even the triplet state is closed, and in this case, basically, you end up with the limiting efficiency of 100% again. Experimentally, these higher efficiencies have been demonstrated by Professor Schmidt and other groups, where when you go to high enough photon densities, you actually reach an efficiency that is at least double or maybe even triple that predicted by spin statistics. And in this case, this is a system based on a porphyrin sensitizer and a very typical high PL quantum yield efficiency emitter rubrine. And these kind of molecules are going to become very familiar to you over the next 15 minutes or so. Professor Schmidt then carried out a rigorous kinetic analysis of this process, and he demonstrated that the conversion efficiency in these systems is about 60%. So that's implying that that at least the quintet, and if not the triplet state, are closed and not accessible when these two triplet states come together. So after giving you the overview of upconversion and what its potential might be, I'm going to show you some of the efforts that have been carried out independently from our group and also within our group towards actually using this for enhanced solar photoconversion. And so straight away I'll show you some work out of the group in Sydney, where they use an transparent amorphous silicon solar cell. They place an upconversion system behind that solar cell and then carry out essentially a differential external quantum efficiency measurement, where in this case they're using a laser diode that's tuned to the absorption band of the sensitizer that basically biases the upconversion system to generate the significant population of triplet states such that you would get under constant illumination. Once again, they use this porphyrin derivative and rubrine as the emitter. They have two different derivatives where the groups at this position are different. They have subtly different absorption spectra, both of which are right around the band gap of the amorphous silicon device that they're working with. And they show that the efficiency increase when the upconversion system is turned on can be modeled very well with the absorption spectrum of the porphyrin sensitizer. They then extended that approach to some transparent organic photovoltaic devices and a modified amorphous silicon device, and used only one of the porphyrin derivatives as a sensitizer. But in all cases, they were able to modify the change in the external quantum efficiency by simply taking into account the transmission of the solar cell, the external quantum efficiency in the absence of upconversion, the absorption spectrum of the sensitizer, and then the absorption cross-section at the bias wavelength. And what you can see here is in the best performing system, they can get around about a 12% increase in the external quantum efficiency, which is reasonable, but not nearly as good as the maximum upconversion yield would predict. Since there has been a little bit of controversy regarding the efficiency of this process and what kind of benefit it could give to device performance, they then came up with a figure of merit. And this figure of merit is essentially the change in short circuit current divided by the solar concentration squared. And what they showed is in their initial efforts with the two different sensitizers, they got about 2 orders of magnitude better performance than the best rare earth system at the time. They then went on to optimize the optics and also optimize the solar cells that they were working with and have seen some steady increases. And this is all within basically a year's worth of work. However, I think they've had some improvements more recently that have, by changing the chromophore concentrations and optimizing the optics further, have got them a little bit better. They made some calculations that if you can dramatically increase the concentration of the sensitizer, you may be able to push up towards the peak enhancement that you observe if you are operating at the maximum conversion efficiency for this system. And that kind of brings me to what kind of approaches can we actually take to maximize this photon upconversion, maximize its impact in a photoconversion system. If we consider the system under steady state illumination, what we find is the fraction of emitters that undergo triplet-triplet annihilation is dependent essentially on the competition between the triplet-triplet annihilation process and the non-radiative decay of the triplet states. And the triplet concentration is dependent on the rate of generation and the concentration of the sensitizer. And so they applied this model for various non-radiative decay rates for the triplet state and found that if you reduce the non-radiative rate, what you can actually do is take a process that has a quadratic dependence and essentially drive this into a regime where you get a linear dependence, at which point you've essentially saturated the quantum yield of the system. Now, to make further enhancements to the existing systems, you can think about trying to increase this generation rate by absorbing more light. And that may mean you need to optimize the transmission of the solar cell, use photonic or plasmonic effects to try and locally increase the concentration of light, and maybe broaden the sensitizer absorption or use multiple sensitizers to try and absorb more of the light that's transmitted through the solar cell. And then the next thing to try and do is to concentrate the chromophores. And I'm going to talk a little bit about some approaches that were in the solid state where you would increase the local concentration of chromophores. But another process that Professor Schmidt has been exploring is absorbing the chromophores onto a surface where, again, you get a local concentration increase. One thing to note is that you could also increase this emitter triplet concentration by decreasing the non-radiative rate, as shown in these figures on the right-hand side. One way to do this, and I'll talk a little bit about this, is to remove oxygen from the system. So oxygen can act as an efficient quencher and actually enhance this non-radiative rate. So in terms of some of the work we've been carrying out in our Sunshot project, we're considering dispersing our upconversion materials into a solid state host. And what I show here is porphyrin complex and diphenylanthracene that have been dispersed in an ethylene oxide epichlorohydrin copolymer. This was essentially the first demonstration that this process could actually be carried out in the solid state. What I may not have made clear earlier on is that the upconversion process itself is strongly dependent on diffusion of the molecules, which is why it happens efficiently in solution. So to actually see this process occur in the solid state is pretty remarkable. But some of the requirements for these polymers is that they have a good transparency. We obviously want to get as much light into them and as much light back out. They need a low glass transition temperature and a high dye solubility. And the low glass transition temperature, we believe, essentially allows the chromophores to move around inside the material. My collaborators then extended the technique to some other low glass transition temperature polymers. These include several commercial polyurethanes, which we can think of as being composed of hard segments that act like physical cross-linkers to soft fluid regions. And these soft fluid regions actually allow the dye diffusion. So they allow the interaction of the chromophores. And what we can see in the three polyurethanes is that as you increase the temperature, the upconversion PL intensity increases dramatically, and this is essentially due to enhanced diffusion inside the system. Finally, my collaborators extended this approach to the same chromophores doped inside another commercially available polyurethane, Clearflex 50. And what they were able to observe in this system is the transition from that quadratic dependence at low power densities to the limiting case where you see a linear dependence, at which point you saturated the conversion efficiency. And they were able to estimate that quantum yield for that process to be around 22%. So not quite as impressive as the 60% that was demonstrated at the University of Sydney, but pretty impressive given that this is the dyes dispersed into a rubbery polymer. And you can see in these photographs here that when you have both dyes present, you convert the green excitation light to blue emitted light. So we can see just by the naked eye the upconversion in these systems. We've been looking at some other systems to try and the previous two compounds that I showed you would not be applicable to a solar photoconversion system because the absorption is in the green. So we've been trying to push the absorption further into the red. The first example here, which would again not be particularly applicable to amorphous silicon or OPV, is this porphyrin derivative, which was coupled with a boron dipyromethane dye. And in that case, you can see red to orange upconversion again in the solid state. They then took a porphyrin with a slightly extended pi system to shift the absorption a little bit further into the infrared and used basically our favorite acceptor molecule, rubrene. And again, they were able to show, in this case, red to orange upconversion, both in solution and again in our Clearflex host polymer. This kind of brings me to the segue regarding the sensitivity of these systems to oxygen. And there are two issues that we need to be aware of. The first is that, as is the case in photodynamic therapy, we can efficiently quench the triplet states that we generate by the presence of oxygen and form singlet oxygen. Another issue with some of the dyes that one might work with, and this is especially the case for rubrene, is they're actually prone to photooxidation as well. And so if there's any oxygen around, if you illuminate them, then you get significant degradation of the materials. And this means that we require either physical encapsulation, as we can see in the plot on the left-hand side. When there is no encapsulation of the system, we see a significant decrease of the rubrene emission. And this is over the course of about a minute. In the encapsulated system, we see that the rubrine emission is essentially constant. But another option for actually preventing the presence of oxygen in these systems is to use a host material that has superior barrier properties. And I show an example here where we have a polyethylene glycol film with no encapsulation. And in this case, we see very little degradation of the rubrine emission. However, this particular system shows very poor upconversion performance, so that kind of suggests that the polymer inhibits both oxygen and dye-diffusion, which is obviously not desirable for the kind of application that we want. But the good thing is that our champion host material also appears to inhibit photooxidation of rubrine. And in this case, our illumination is over the course of about 2 hours, and we see no degradation of the rubrine emission. So it appears that this ClearFX 50 actually is a good candidate for a host material that may or may not require encapsulation for an overall device. So now I've shown you how we've been targeting high enough concentrations to enhance the upconversion yield. I'm going to talk a little bit about some of the systems we've been developing to target infrared to visible upconversion. And these are focused on amorphous silicon devices, but this approach is also applicable to a lot of OPV devices. And if we look at the external quantum efficiency of an amorphous silicon device, we can see that our sensitizer absorption needs to span from about 700 to as far into the infrared as is possible, and that the emission should peak somewhere in the 550 nanometer regime, which is right where rubrine emits, so that's why it's been our favorite acceptor molecule. So the approach we've taken to extending the spectral response has been to construct these what we call supermolecular triplet sensitizers. And these are built up from metal terpyridyl complexes and metal porphyrins. They have tunable, strong near-IR absorption bands, and they rapidly intersystem cross and give long-lived triplet excited states. And here's an example of one of these complexes. You can see it has strong absorption between 650 and 800 nanometers, so pretty good for an amorphous silicon device. This system has been used in conjunction with 2 different acceptor annihilator molecules. And in the case of the parylene derivative, we see typical quenching behavior, and at high light intensity, we see a conversion from the quadratic to linear dependence, indicating we're saturating the efficiency. For rubrine, we see the same behavior, good quenching, conversion from quadratic to linear, and we can see by the naked eye infrared to visible upconversion. And this is also visible in our ClearFlex polymer. One of the issues we have, a benefit of this system is actually that they're composed of modular building blocks, so depending on the exact linkage of these components, we can tune the lowest energy absorption band. But that actually proves to also potentially be a drawback, because in the system that we've so far demonstrated our most redshifted absorption, we also have a low triplet quantum yield. And what we think is happening in this system is we've actually pushed this lowest energy band that's associated with this porphyrin moiety below the triplet excited state that we'd like to transfer the energy from to our acceptor. And so we now have a loss pathway for those triplets. We have a few different approaches to mitigating this issue. One is to replace the metal atom in the metal terpyridyl complex, and that may allow us better control over the relative energies of these systems. We can see that the absorption band is basically unaffected, but our preliminary experiments suggest that this actually does give us better control over the relative positions of these and maybe gives us a higher triplet quantum yield. We've also been considering that the fact that you need to have solubilizing groups on these chromophores to disperse them into solution requires this type of group. And depending on the attachment of these chains onto those solubilizing groups, basically can force this ring out of the plane of the porphyrin system and provide steric hindrance to the acceptor coming close enough to the chromophore to get efficient triplet energy transfer. And so we're exploring the behavior of these two systems and looking at their upconversion performance. And then finally, what I would have liked to have shown you is demonstrated some of these systems in a coupled upconversion PV system. We are in the process of carrying out those measurements, but I don't have anything to show you right now. But one final thing to think about is the process is dependent on the concentration of light. And one way that we can think about doing this is the solar cells that we're targeting typically don't function very well under concentration. And so we can think about using plasmonic effects to basically create a local solar concentration inside the upconverter system. And these are some calculations carried out in Jennifer Dion's group at Stanford, where they demonstrate an enhancement of the power directed back into the cell of between 10 and 1,000 over a pretty wide spectral range. So maybe this is a good method to get the local concentration of light and even potentially direct those photons back into the solar cell. And with that, I hope that I've demonstrated that molecular photon upconversion is a viable strategy towards enhancing PV devices. I've shown that the work out of the University of Sydney group has demonstrated experimentally that this is possible, but that there is still significant progress to be made. I've shown that our work on our Sunshine project can extend the response of the system further into the infrared, and that we can incorporate these dyes into solid-state hosts that still demonstrate reasonably good upconversion. And that maybe the final push towards that maximum performance enhancement is going to require photon management strategies such as photonic or plasmonic elements. And with that, I thank you for your attention, and we'll try and answer any questions you have.